I understand that you work with the with quantum computing on AWS. Can you tell us a little bit more about your role and what you have been working on recently?
Yeah, absolutely. Yeah, I work in Amazon Bracket as a tech evangelist. So I'm really primarily interested in understanding how people use Bracket in their research and experiments and trying to make the service better for everyone to be able to make the best use of like a really exciting emerging technology.
Now, you say emerging technology. I know that Amazon Bracket is quantum computing, but I'm going to be honest, I don't really know that much about Amazon and quantum computing or even quantum computing in general. So I'm counting on you to sort of educate us a little bit on the basics of what is this quantum computing stuff and, what is the announcement today about Amazon Bracket that folks should be excited about?
Yeah, absolutely. So the basic idea of quantum computing is really easiest to understand if you think about classical computing first. So, classical computing is just regular computers. They call them classical to differentiate from quantum. There are different types of physics that apply at different scales. And so, in quantum computing, whereas the fundamental unit in a classical computer is a bit, so one or a zero, the fundamental unit of a quantum computer is a quantum bit or qubit. And so the fun sort of analogy that often comes up in quantum mechanics is Schrodinger's cat, which is like the cat that's both alive and dead at the same time because it's like in a box with a nuclear isotope that might decay and might not, but you don't know until you observe it. So quantum mechanics is this way on a very small scale, and actually it goes up to larger scales. We're actually not sure exactly what scale it stops working on. They're the kind of fun intermediate theories that people work on. Um, but basically, in a quantum computer, you can have what's called a superposition of not just one or zero, but also essentially this weird state that's both at the same time, just like Schrodinger's cat. And so superposition is also sometimes called coherence. And so due to superposition and also due to another weird thing called quantum entanglement, which is actually what Einstein called spooky action at a distance. Essentially, if you bring two identical particles really, really close together and then you take them far apart to opposite ends of the universe, they are still intrinsically linked somehow. If you measure one of them, you instantly know the results of the other one's measurement, which is really weird. And so that is those are a couple of aspects of quantum mechanics that make quantum computers different than classical computers. And then the last one is quantum interference, and this one's a little bit more difficult to explain, but essentially on a very small scale, everything everything exists in these superpositions, and the way that we think about them and the way that we write them down mathematically is with what's called a wave function. And so these are actually really mathematically the same as waves on the ocean or waves in like sound waves. And so you can actually have states that interfere with each other either destructively or constructively. So destructive interference would be like a wave coming up and then a wave going down, and they crash together, and it's flat. So you can have this. It sounds strange, but you can actually have this with quantum states. So a state could be interfering with itself actually, or it could be interfering with other quantum states. And so it makes certain possibilities for, let's say, like the position of a particle, uh, basically impossible, because the probability in the wave function destructively interferes for that particular possibility. And if this all sounds kind of crazy, I know. It's a very challenging field. Yeah.
Jason on LinkedIn says Jordan is blowing my mind right now, which I 100% agree with.
Yeah.
I've worked with those bits, I've worked with those ones and zeros all my life. So hearing the fact that you can have a bit, in this case a quantum bit or qubit, that is not one or zero, but it could be a one or a zero. Or we're not sure yet. And hearing about this interference is truly fascinating.
Yeah, that was a great summary, Jordan, and I still probably understand about 10% of what you said. But so what problems do we think we can solve with quantum? Like what's the application?
Yeah, that's an excellent question. So actually, the original reason that quantum computers were sort of proposed as even a concept was by the physicist Richard Feynman, and he essentially said something along the lines of, well, if you want to accurately simulate quantum mechanics, you're probably going to need a computer or a system that is quantum mechanical itself. And so one of the major applications that we think is going to be like the earliest one is in quantum chemistry. So this is things like simulating chemical interactions, chemical reactions. And so you could do things like simulating protein folding, which is involved in drug development, and also simulating things like carbon sequestration for combating global warming. And so those are a couple of quantum chemistry applications. And the other one that quantum computing is really well known for is what's called Shor's algorithm, which can break the encryption that is used to secure basically the entire internet. Um, and that sounds really scary, but rest assured, you need a quantum computer that has millions of qubits in order to actually run Shor's algorithm. And at the moment, we're sitting at like 150 maybe, and they're not error corrected. That's actually a really important point because in order to run these really exciting sort of full-scale applications like breaking encryption and simulating simulating protein folding, you need what's called a fault-tolerant quantum computer. And so essentially, it needs to be so much bigger because you need a ton of extra qubits in order to do quantum error correction. So quantum error correction is, it takes its origins from classical error correction again. And the very most basic way that you can think about error correction and the simplest error correcting code is just repeating the message over, right? So if I wanted to send you a 0, but I thought maybe it could get messed up somewhere along the way, then I could just send you 3 copies of a 0, and then you just take the average, and whatever is the whatever's the average of that, that's probably what the original message was. So unfortunately, you can't do this in quantum computers. You can't just send extra copies of the same thing because of what's called the no cloning theorem in quantum mechanics. It's just not allowed. Every operation on the quantum mechanical level has to essentially have the same number of inputs as the number of same number of outputs as the number of inputs, and so it's just not allowed that you can clone things. So you have to do something that's a little bit more clever. And so what we do is we entangle many different qubits together in really specific ways so that they collectively correct errors in the overall, what we think of as a logical qubit sometimes. And that's
So if
the
I
overall
understand it correctly, having more of these bits allows us to get better results because you can entangle them, right?
Mm-hmm.
Fascinating.
Yeah. But unfortunately, the only way that this works is if your very like low level errors. So like, let's say the errors that you have in entangling 2 qubits. So the errors like on a chip level. If those errors are low enough, then you can do this. You can increase the size of your machine. You can entangle more and more and more and more qubits. And your overall error rate of your whole computation that you want to do will be suppressed exponentially. This is called the threshold theorem. And again, that's kind of a weird thing. Like that's a quantum
I
mechanical thing.
I just thought of something I wanted to circle back to because
Yes.
it reminded me of something you said earlier about the protein folding.
Yeah.
I remember reading that when researchers were trying to research COVID, one of the ways that they investigated like protein folding associated with the virus was they actually farmed the jobs out to a ton of gamers, and they essentially made like a game which would have like people, a whole bunch of people manually folding these proteins and trying to figure out. And it was very intensive. They said like these people spent a total of millions and millions of hours folding these proteins to try to find the result as part of this research for COVID. So if I
Mhm.
understand correctly, what you're saying is that the quantum computer and quantum mechanics could help solve this type of problem potentially radically faster. Maybe it won't require millions of people to fold
Yeah.
proteins manually.
Yeah, exactly. So when we have these full-scale fault-tolerant quantum computers, which is the ones with a lot of entanglement on many different qubits and really low error rates, then yeah, we'll be able to solve problems like protein folding. We'll be able to fully simulate the quantum mechanics of these, chemical reactions, and yeah, that's a really exciting thing. That's still a little
Now,
ways out. At the moment, we're in what's go ahead.
so you said when we have these computers. So I assume what you mean is we don't quite have these computers yet, but we're getting there.
That's
And so I think that comes into like with the announcement for this
Mhm,
particular segment. My
mhm.
understanding is we are getting closer to having some more interesting computers. What are we actually launching today?
Yeah. So basically, we're in the era right now that's called noisy intermediate scale quantum, or NISQ. And this is the point where we have, on the order of like 100 qubits or so. They're not error corrected, but you can still do some interesting sort of experiments on them. And it's quite possible that you could actually do something useful on it. We just don't know yet of any sort of guaranteed applications that we definitely do know about for large full-scale quantum computers. And so today the launch that we're announcing is with one of our partners, Rigetti, and they have just released an 80 qubit quantum computer, which is available on Amazon Bracket. And you are able to access it just with a regular AWS account. You don't need a contract or anything. You can just get up and running and run on a real quantum processing unit.
that
And so
sounds
Wow.
they
cool.
yeah, they launched just this past Tuesday, February 15th, 2022. And for anybody who is curious, the existing Rigetti chip that's on Bracket right now, the Aspen 11, that will be retired on the 1st of March, and it'll be replaced with the 80 qubit version, which is double the size, which is quite exciting.
Okay, so we've talked a lot about the theoretical mechanics of quantum computing, and you've announced that there is now an 80 qubit quantum computer available on AWS. My understanding is there's something you can show us as a demo
Mhm.
of
Yeah.
how what the experience is to interact with a quantum computer, because I'm visualizing a lot of very sci-fi type of scenarios, but
Yep.
what does it look like today?
Yeah. I will go ahead and start my demo here.
Yeah, if you could share your screen. I'm not seeing your screen yet, so there
Yeah,
we go.
it should show up here. Okay.
Okay.
Yeah. So I know it does all sound very sci-fi, but I'm just using Jupyter, so it's it's a little bit more down to earth than it might seem at first. So yeah, at the moment I'm going to be showing you some of the uh, examples. Oh, I'm going to be showing you an example notebook from our Bracket examples, which you can find on GitHub, in our repo. And in particular, the application that I'm going to be showing you today is one that I actually haven't talked about yet, but it's a way that you can use quantum computers to get quadratic speed up over classical computers for the task of optimization. And in this particular case, the problem that I'm going to be trying to optimize is what's called the max cut problem. And the easiest way to explain this is um, we want to think about a graph. So I've just randomly generated a graph here. And so the max cut problem, I like to think of in terms of, let's say I had two electronic chips and I have to separate them some way because I can't fit all of my circuits on one. But I want to minimize the number of wires that have to go back and forth through the different chips because that can cause problems. And it's just harder logistically. So the max cut problem is about, well, it's actually the inverse of this, but essentially in the inverse of the max cut problem, you would want to minimize the number of connections that you have between your two circuits. In max cut, it's just the opposite of that. So you want to maximize the number of connections between the two sides of your circuit in my example. So in this case, for this small graph, we want to separate all of the nodes of the graph such that uh, there's the maximum number of edges that go through that slice. And it's a little bit difficult to picture all of this, but suffice it to say, it's an optimization problem and it has quite a lot of practical applications. So we will go ahead and put in the input data, which is essentially the way that this works is that the quantum computer, or we reframe the max cut problem in terms that the quantum computer can kind of understand. And so we frame it in terms of, this will make it sound like it's making it more complicated, which it is for people, but it's less complicated for quantum computers. So we frame this max cut problem, which is in terms of graph with edges and nodes, in terms of an energy. So we think of the lowest energy state is our solution. So this is just like kind of classical machine learning, where we're trying to minimize some sort of cost function and end up at the bottom. So in this case, the cost function that we're trying to minimize is the overall energy of this system. And we want to encode our max cut graph problem in a way that it's encoded in the energy of a system, which is the language that we can talk to our quantum computer in. And don't worry if you didn't follow all of that. It's hard for me to understand this stuff a lot of the time too. So
we have a
um,
comment along those lines from LinkedIn just now. He says that he really he's feeling like a dummy and wants to get practice and learn AWS. But my understanding is like this is a very new field, and there's a lot of
yes.
people who want to learn this. And getting access to these computing devices in order to run these workloads could be traditionally quite challenging. But now, if you have an AWS account, you can actually sign up and start to learn from some of these materials, such as what Jordan is putting together in this notebook, to learn what is this quantum computing thing? What are these hyperparameters that I see referenced, and how do I start to use that? So the learning capacity is there now that you have access to the tool to actually play around with the quantum computer.
Yeah, that's a great point. The other thing is there's a whole repo that you can get access to, well, that you already have access to. It's just on GitHub, and this is way too small. Okay, there we go. This is this bracket tutorials GitHub. It's just called Amazon Bracket Examples. And so there's all of these great tutorials on getting started with simple circuits and algorithms. And I should say the demo that I was showing, and well, I'm going to continue showing after this, is like an advanced quantum circuit. So again, don't worry if it's like very confusing at first. It takes practice to get your mind to kind of think in these ways. So yeah, there's all these sorts of, if you want to learn more about quantum computing, all these great resources.
For sure. We just want to show off that advanced example clearly to fully stress the capabilities of a 80 qubit computer, quantum computer.
Yeah. So this bit, this is specifying, actually, I don't know why these are two separate cells. They're kind of separate things. Okay. This is where you can specify the device that you want to be using. And now this is a really cool aspect of Bracket because all of the code stays the same regardless of whether you are using say a quantum computer simulator or a real quantum computer. And on Bracket, we have actually multiple different quantum computers of different types, and Rigetti is one of them. And so if you log onto the Bracket console, you land on this devices page. So there are these couple of D-Wave devices, which are quantum annealers, totally different type of quantum computer. And there's an ion-based quantum computer, and then there's these two Rigetti devices. And then this one, the Aspen M1, is the newest one. And so if you click on it, like you can see the way that the qubits are all laid out, and it tells you about when it's available, as well as the cost.
So
And the region as well.
I've got a question
Yes.
that maybe will help viewers to better picture what we're dealing with here. You say there's
Yep.
different types of quantum computers here. Do you have a picture of what the quantum computer actually looks like as a physical
Sure.
device?
While you're pulling
Yeah.
that up, I have a funny comment.
Mhm.
I don't know if we
Oh.
have a different version of this, but
I'll need Bracket for Dummies.
I'll need that too.
Yeah, we all need it.
Let's see. Maybe Google has some pictures. Google. Yeah, here it is.
Ooh,
Open.
interesting.
Open. I'm always trying to click the right thing here. Maybe
Yeah, if
that'll
you
be easier.
open a new tab, should be able to zoom in all the way. We'll see it larger.
The words are just very small. Okay, here we go.
Okay, interesting. So this reminds me a lot of when the early days of classical computing, when computers were these gigantic cabinets full of vacuum tubes.
Yep.
And it was this huge physical device, but it was only storing like a few kilobytes of memory. It was only being able to do a few operations per second. And what I'm seeing here, it's reminding me. I see these like a very large physical device. Actually, it's not a tiny processor. It's a large device that has a lot of material there.
Yeah, and we are very much in that sort of really early stage of quantum computing, which makes it a really exciting time to be involved in the field in this very sort of ground floor way, and being able to try to figure out what sort of applications will be ultimately useful. And like that's the really crazy thing about quantum computing is that we already know of legitimately like mind-blowing, world-changing applications for full-scale quantum computers, but we don't even have them yet. And so the amount of things that you could imagine people before we really had microprocessors trying to imagine all the things that you could use them for, it's just impossible. Like what we will ultimately use quantum computers for, I think that there are just a lot of applications that we haven't thought of yet because we don't have these machines to play around with. And so these early NISQ devices are really a really neat opportunity to be able to experiment with and try to find earlier applications. And you can do that with Amazon Bracket.
That's fascinating. Yeah. So like in the early days of classical computing, if I didn't have access to a computer, I couldn't be a computer scientist. Likewise, today with quantum computing, it's so different from traditional computing that it's going to be hard for me to learn the science behind it and learn the concepts if I don't have access to an actual quantum device. And now through AWS Bracket, I'm getting access to not only quantum devices but larger 80 qubit devices as well.
Yep, exactly. All right, so jumping back to our tutorial here, when you want to like use Bracket, you can basically all you need to do is specify the ARN or Amazon resource name of the device that you want to use. So like, let's say I want to use the brand new Rigetti 80 qubit M1 device. All you need to do is just copy the ARN right here and then paste it in, which I already have up here, but if I wanted to, I could just, oops, Stacy, not that. I'm always pressing Alt and not Control. Yeah, so that's all you need to do, and all of the code that you actually use to interact with the circuits is all identical. I'm going to leave it on Aspen 11 right now because actually the availability window, currently Aspen M1 is not online. This is when you can see its next available is in like 17 hours, whereas the Aspen 11 device is available now. So I'm going to use
Interesting.
that for this
So
demo.
what does it mean for availability window? Like, I'm used to traditional computers where, if I want to be highly available, I can. Why does the Rigetti have an availability window? Like, what is happening during the downtime when the device is not available for me to use?
Yeah, it's a really good question. So one of the reasons that they have these availability windows is because we're in this noisy intermediate scale of quantum computing. And so what happens is every so often, say every like 4 hours, they need to uh, recalibrate the quantum devices, because what happens is I mentioned earlier that the superposition state where qubits can be a 1 and a 0 at the same time. Like I said, this is sometimes called coherence, and there's a certain type of error called decoherence, where essentially the the sort of delicate superposition state just begins to degrade over time due to interference from uh, random cosmic rays, or bumping the table, or all sorts of things can cause quantum states to decohere. And so basically you kind of just need to recalibrate and reset these qubits in order to get the best fidelities, so the best performance basically out of your quantum computer.
Peter commented, it said that quantum devices today are not just sitting in the corner and doing their job quality; they're demanding a support team is needed to keep them operational.
Yes.
So this is like an early stage device. It's just like going back to the classical computing again, those vacuum tubes. A lot of those old devices would have to be maintained constantly. The term for like bug came from a actual insect got
bugs.
into the computer, and the insect like fried a circuit and the computer broke, and they're like, oh no, the bug hit the computer. So
Yep.
to me it sounds like quantum is in that same phase where these physical devices are a little bit fragile right now. They're not super easy to work with. They have to be reset, but you can start to interact with them now using AWS Braket.
Yep, exactly. Yeah, so going along with our demo, this next bit is just specifying hyperparameters. All of these are actually, um, they're more for the sort of classical machine learning aspect of the demo that we're doing. And so the next bit is just specifying the region, and then specifying this interface. These are basically just different ways of getting the gradient, basically just different APIs for doing machine learning. And with the plugin that I'm using, which is PennyLane, which is a quantum machine learning plugin, and they're also one of our partners. They have the ability to use AutoGrad or Torch or TensorFlow as the interface for the machine learning part. So next is the submitting a Braket job. And this is a feature that we launched late last year on Braket, and it allows you to essentially do these back and forth calls from your classical computer to your quantum computer, back and forth. And this allows us to essentially use classical machine learning in order to correct for the types of errors that we get in classical in the quantum computers, so that the ultimate measurement outcomes at the end of the job are more accurate. And so there's just description of the different arguments that you need to input for a bracket job. Yeah, we don't really need to go into these in detail, but the most important, whoops, daisy, most important being that you specify the device and the source module, which is the actual job that you're trying to run. And so then you can just create the job using this AWS job create command. Haha, it doesn't want to do that apparently. Let's see. Why is it mad at me right now? Parameter validation failed.
Where's
Invalid
that operations team, right?
hyperparameters. Yeah. Oh, okay. Maybe like this. It wants it to go back to 2. Let's see. I tried adding more layers to the. Okay, it likes me now. Yeah,
Okay.
I had tried to add. Yeah. Okay, so I had tried to change the hyperparameters a little bit for the yeah for the words are not helping me right now. I was trying to change the hyperparameters for the algorithm, and it was not a fan of my choice because it didn't work. I think with the number of edges and nodes in the graph that I had chosen. I was playing around with different graph sizes today, so yeah. Moving on, we can check the job state.
So what this did, if I understand it correctly, is it created a job and it submitted it to Amazon Bracket now.
Yes,
So the
exactly.
job is now queued up to run on this Rigetti device the next time the device comes out of its availability window. It gets like reset and calibrated, and it's ready to run a quantum computing job.
Yeah, so basically, first I've actually specified the in the device up here, I've specified Aspen 11, and now that is actually the one that's currently online,
Oh, okay.
as we can see here.
So we don't have to wait for that one.
Right, we don't have to wait for that one in order to actually see that it's running. And so we can check that is indeed saying that it's running. And then we can also check that same thing if we just make sure we're in the right region, and Northern California is the right region for this particular job or this particular device. That's where Rigetti is located. They're in Berkeley. And actually, this is a task that I ran earlier that has now finished. And so I can probably, this will be, we'll see exactly how good this data is. It might be very noisy. So if it is, then it's very noisy. We're in the early stages of technology, are we not? So one moment here, we can plot the outcome of this guy. So in theory, what should be plotted here is the outcome of the optimization for the cost function. So you would hope to see the cost function going down as you iterate on your passing back and forth between the quantum and classical layers, and it does go down slightly. So that's good. It's kind of optimizing. So that's nice. We can also compare to a couple of other jobs that I ran earlier. There is the same thing that I also ran on IonQ, and we can see the results of the optimization over the iterations in this one as well. It just takes a couple of seconds to actually plot. And so it should be almost ready. And this one also goes down slightly, so that's exciting. Another quantum computer. Like, it's hard to emphasize this enough. Like, this looks like it's really sort of straightforward because we're all just running things in Jupyter, cells. But, I've accessed an ion trap in a lab in Maryland to run an algorithm, like a quantum algorithm, and then I just changed like one line of code and did the same thing on a superconducting qubit, in Berkeley, which is crazy. It's very kind of mind blowing.
That is pretty awesome because traditionally if I wanted to access one of these devices, I imagine I would have to go the university route, find the university program, get credentialed access because I'm sure these devices being very fragile and new are like behind layers of security, right?
Hmm.
I can't just walk in and be like, well, let me start interacting with a quantum computer.
Yeah,
I'm gonna
exactly.
have to get approval to actually get access to the device, and now
Hmm.
I can interact with it over the internet via an API
Hmm.
provided by the Amazon Bracket API.
Yeah, exactly. And so just to show you as well, if I wanted to run on the brand new device that was just launched, the Aspen M1, I'm just gonna uncomment this line. Device is Aspen M1, and I create the job, and we shall wait to see what the job state is. If all goes well, it should say queued, and it says queued. So again, we can go back here to jobs, and again, we're in the right region still. And we can see that this job is queued, and this is the device that it's running on, the M1. And yeah, that is basically the demo.
That is really fascinating. I think everyone still has a lot of questions about quantum. Everybody's trying to understand it. But I think this comment from Tomas kind of encapsulates a lot of us probably feeling that we're sitting here pretending to understand. But I think the aspects that I certainly do understand is that these quantum devices are exciting. They're brand new tech that has a lot of possibilities, and it's not easy to get access to a physical device, hands on, obviously, because they're spread out at different locations around the world. They require a lot of maintenance, but I can actually interact with one over the internet via an AWS API, and that's really exciting. And the fact that now there is an 80 qubit one, which is quite large, like that's very very exciting.
Mhm. Yeah,
So thank
absolutely.
you very much, Jordan, for joining us today and giving us this master class on quantum computing and Amazon Bracket. And I'm really excited to see where this technology goes.